In 1964, a physicist in Geneva conducted an experiment so simple it could be described in a single sentence. The result of that experiment has never been fully explained, and it implies something about the nature of time that most people are not prepared to accept. His name was John Stuart Bell, and the experiment he designed was meant to settle a debate that had divided the greatest minds in physics for 30 years. The debate had started in 1935. Einstein on one side, Niels Bohr on the other, and at the center of it, a question so fundamental it sounds almost childish. Does reality exist when nobody is looking at it? Einstein said yes, of course it does. The moon is there whether you look at it or not. There must be hidden variables, things we haven't measured yet, that determine the behavior of particles before we observe them. Bohr disagreed. Quantum mechanics, he argued, suggests that particles don't have definite properties until they are measured. Reality at the quantum level is fundamentally indeterminate. This wasn't a philosophical argument. It was a disagreement about the fundamental nature of physical reality, and it had no experimental resolution. Until Bell's theorem showed that if Einstein was right, if hidden variables existed, then experiments involving pairs of particles would produce results within a certain statistical range. If quantum mechanics was right, if particles truly had no fixed properties before measurement, the results would exceed that range. Violated. Statistically, impossibly, the experiments were run, the results came in, and they violated Bell's inequality. Consistently, reproducibly, across dozens of independent laboratories, Einstein was wrong. Hidden variables don't explain what particles do. Reality, at the quantum level, genuinely does not have fixed properties before measurement, but that result comes with a consequence that Bell himself found deeply uncomfortable, a consequence called entanglement. Quantum entanglement occurs when two particles interact in such a way that the quantum state of each cannot be described independently of the other, no matter how far apart they are. Measure one particle and instantly, not eventually, not after a signal travel, instantly the other particle's state is determined, regardless of the distance between them. Einstein called this spooky action at a distance. He used the phrase as a dismissal, as evidence that quantum mechanics must be incomplete. He died in 1955, still convinced that quantum mechanics was missing something. He never saw the Bell test experiments. He never saw himself proved wrong, but here's where the story becomes genuinely strange. Because entanglement doesn't just challenge our understanding of space, it challenges our understanding of time. In 2012, physicists at the University of Vienna conducted an experiment that took entanglement one step further. They called it entanglement swapping with delayed choice. The setup, two pairs of entangled particles. Particles 1 and 4 are sent to separate detectors. Particles 2 and 3 are held in the middle. Particles 1 and 4 have never interacted. They were created separately. They share no history. They have no reason to be correlated. Particles 1 and 4 are measured first. Their results are recorded. Then, and only then, particles 2 and 3 are measured together, creating entanglement between them retroactively. The result, particles 1 and 4, which were measured before the entanglement was created, showed correlations consistent with entanglement. Let that settle for a moment. The measurement happened before the entanglement existed, and yet the measurement reflected the entanglement. This is not an interpretation. This is not a theoretical prediction. This was observed in a controlled laboratory, published in a peer-reviewed journal, replicated. The future, a measurement that hadn't happened yet, influenced the past. The present state of particles was determined by something that hadn't occurred yet when they were measured. If you find yourself wanting to reject this, that reaction is correct, because this result is incompatible with every intuition about cause and effect that evolution has built into the human brain. We experience time as a river. It flows one way, because precedes effect. The past is fixed, the future is open. This is not a philosophical position. It feels like a physical law, but the quantum world does not share that intuition. And the quantum world is the actual world. The large-scale world we experience is built from quantum components. So how does the arrow of time emerge from a quantum substrate that doesn't seem to respect it? This is one of the deepest unsolved problems in physics. To understand the answer, or at least the current best attempt at one, we need to go back further, to the laws of physics themselves. Here is something most people don't know. Almost every fundamental equation in physics is time-symmetric. Run them forwards or backwards, they work equally well. Newton's laws of motion, Maxwell's equations for electromagnetism, Einstein's general relativity, Schrödinger's equation in quantum mechanics, all time symmetric. If you filmed a pendulum swinging and played the film in reverse, you couldn't tell the difference. The physics works both ways. But if you filmed a glass falling off a table and shattering, and played it in reverse, you would know immediately. Shattered glass does not reassemble itself and leap back onto tables. Why? The physics allows it. The equations permit a universe in which shattered glass reassembles. So why doesn't it happen? The answer is entropy. And entropy is the closest thing physics has to an explanation for why time flows in one direction. Entropy is a measure of disorder. And the second law of thermodynamics states that in any closed system, entropy always increases over time. Order becomes disorder, never the reverse. A drop of ink in water disperses. It never spontaneously reassembles into a drop. A scrambled egg cannot be unscrambled. A fire reduces wood to ash, never the other way. This is the arrow of time, not a law written into the equations of physics, but an emergent property of statistics. A consequence of probability so overwhelming it feels like a rule. There are more ways for things to be disordered than ordered, vastly more. And so, disorder increases, not because the laws of physics demand it, but because the odds are incomprehensible. But here's the problem. The Vienna experiment, and others like it, that suggest that at the quantum level, this statistical arrow may not be absolute. That under specific conditions, quantum systems can exhibit what physicists call retrocausality, the influence of future events on past states. Retrocausality is not time travel in the science fiction sense. No object moves backwards through time. No information is sent to the past in any usable way. But correlations between particles, the statistical fingerprints of their interactions, behave as if information from the future influenced the past. This is not a fringe interpretation. Some of the most respected physicists in the world take retrocausality seriously as a possible feature of quantum mechanics, including Hugh Price at Cambridge, Rod Sutherland in Sydney, and a growing number of quantum foundations, researchers who argue that retrocausality may actually simplify quantum theory, that instead of requiring bizarre interpretations like many worlds or wave function collapse, retrocausality offers a cleaner picture, one where time is genuinely bidirectional at the fundamental level. But before we go further into the implications, we need to understand the experiment that started all of this more carefully. Because the details matter, the double-slit experiment. If you know physics, you've heard of it. If you haven't, pay close attention, because this is where reality starts to behave wrongly. Fire electrons, one at a time, at a barrier with two slits. On the other side, a detector records where each electron lands. What pattern do you expect? Two bands, one behind each slit, like bullets through two windows. That's what you'd expect if electrons were particles. What you get instead is an interference pattern. Multiple bands, alternating light and dark. The pattern you'd expect from waves, not particles, even when the electrons are fired one at a time, with no other electron present to interfere with. Each single electron somehow passes through both slits simultaneously and interferes with itself. This is superposition. Before it is measured, the electron exists in a combination of all possible states simultaneously. It is not in one place. It is in all possible places at once, weighted by probability. Now watch what happens when you try to observe which slit the electron passes through. The interference pattern disappears. The moment you measure the electron, it stops behaving like a wave and starts behaving like a particle. Two bands, no interference. The act of observation collapsed the superposition. The electron knew it was being watched. That sentence is physically accurate and philosophically catastrophic. Now take this experiment and apply the delayed choice variation, developed by physicist John Wheeler in 1978. Wheeler asked, what if you wait until the electron has already passed through the slits, and only then decide whether to measure which slit it used? If you choose to measure, the electron, which has already passed the barrier, retroactively behaves as if it went through one slit. The interference pattern is gone. If you choose not to measure, it retroactively behaves as if it went through both. The interference pattern remains. Your decision, made after the electron passed the barrier, determined what the electron did when it passed the barrier. This experiment was conducted not as a thought experiment. In 2007, a French team ran it with photons. In 2015, it was run with helium atoms. The result was the same. The past behavior of particles is influenced by future measurements. This is not an interpretation. This is a measured, confirmed, reproducible experimental result. Now let's scale this up, because Wheeler didn't stop at laboratory experiments. He proposed a cosmic version. Light from a distant quasar, billions of light years away, bends around a galaxy acting as a gravitational lens. Two paths, both reaching Earth. The photon takes both simultaneously. If we choose to measure which path the photon took after it has already traveled billions of years, the photon retroactively took one path, billions of years ago. Our measurement today is, in some sense, influencing the behavior of that photon billions of years in the past, before Earth existed, before the solar system formed. This is Wheeler's delayed choice experiment at cosmic scale, and it has been observationally supported by studies of gravitationally lensed quasars. The universe, at the quantum level, does not seem to have a fixed past until the present moment creates one by measuring it. History, in some sense, is being written as we observe it, not metaphorically, physically. There is a concept in quantum mechanics called the block universe, or eternalism. The idea that past, present, and future all exist simultaneously. That time is a dimension, not a flow. In a block universe, the past is just as real as the present. The future already exists, and what we call the present is simply the location of our consciousness along the time axis. This view is mathematically consistent with relativity. Einstein himself believed in it. He wrote about it explicitly in letters to friends near the end of his life. He said, "The distinction between past, present, and future is only a stubbornly persistent illusion. But if the block universe is correct and time doesn't truly flow, then why do we experience it as flowing? Why do we feel the present moving? This is called the problem of the now. And it is one of the hardest problems in the philosophy of physics, because physics cannot locate the present moment. Every observer in the universe has their own present moment, shifted relative to every other observer's present by their relative motion and gravitational field. There is no universal now. Simultaneity is relative. What is present for you is past or future for someone moving at a different velocity. This is not theoretical. GPS satellites experience time at a slightly different rate than we do on Earth. Without correcting for this, GPS systems would accumulate errors of 11 kilometers per day. They correct for it every day. Time dilation is not a laboratory curiosity. It is a real effect that engineers account for in the technology in your pocket, so time is relative. The present is personal. Entropy creates the direction, and quantum mechanics suggests the past may not be fully fixed. What does this mean for consciousness? For memory? For the feeling that you are moving through time rather than time moving through you? Some physicists argue that consciousness itself may be fundamentally tied to the arrow of time, that the experience of time flowing forward is what consciousness is. That memory, the record of the past, is what creates the asymmetry. A system with memory experiences time as flowing forward. A system without memory would experience no direction at all. This connects to a deeply strange possibility. If retrocausality is real, if the future genuinely influences the past at the quantum level, then in some sense the future is always already shaping what we are right now. Not in any way you can use, not in any way that gives you information about what will happen, but in the structure of quantum correlations that underlie everything you experience. In 2022, the Nobel Prize in Physics was awarded jointly to Alan Aspect, John Clauser, and Anton Zeilinger for experiments on entangled photons that definitively confirmed the violation of Bell inequalities. The Nobel Committee explicitly stated that the work proved that nature is non-local, that quantum particles can be correlated across any distance with no signal passing between them. Non-local. This word is important. It means the universe does not operate entirely within the constraints of space and time that we observe at the human scale. Something connects those particles across space. Something connects measurements across time. And that something is not a signal, not a force, not anything physics has a complete name for yet. Physics is comfortable with not having the answer. What it is not comfortable with is pretending the question doesn't exist. And the question, stated plainly, is this: is time real? Does it flow? Does it have a direction built into the laws of nature? Or is the river of time something the universe creates only when it is observed? We don't know. But we know more than we did in 1964, and what we know is stranger than what we feared. The experiment that Bell designed was simple. 2 particles, 2 detectors, a statistical comparison. It took less than an afternoon to set up. What it revealed took 60 years to fully absorb, and we are still absorbing it, because the implication is not just that quantum particles are strange. The implication is that time, the thing that organizes all of your experience, all of your memories, all of your plans, is not what you think it is. It is not a river. It is not an arrow. It may not flow at all. It may simply be a feature of how large-scale systems, including brains, process information, a story that entropy tells, convincingly, persistently, so convincingly that no human being in history ever seriously doubted it, until the experiments began. And even now, knowing what the experiments show, you will walk out of this video and experience time exactly as you always have. Forward, irreversible, real, because at the scale we live, entropy rules. The statistics are so overwhelming that the bidirectionality of the quantum world never reaches us. It stays hidden, down in the dark, in the correlations between particles, but it's there, in every atom of everything you touch, in every photon that reaches your eyes, in the particles that make up the neurons firing as you understand this sentence. Time runs forward for you, but the physics that makes you possible doesn't know that.